So this is our last step of where we've been. We're doing integrins and the steroids, the nuclear receptors, I should say. Integrins are adhesion receptors. So those are the fifth and sixth classes of the receptor pathways that we've done so far. Of the single cascades, I should say. So you can see where we're at in the little picture outline that I like to use. And remember, we're comparing and contrasting. I'm now starting to sound like some of our politicians. Just make up words. Alternative fact. I wasn't going to say anything, but yeah, that's one of my. Well, I just always like the way that George W. Bush a lot of times would make words. Like the English language is an expanding language. It's not a dead language anyway. So I had a roommate that was a linguistics major in college. So I got to hear, oh, we're gonna hear it again. Yeah. All right. So once again, one way that the integrins, I'm going to say that instead of adhesion receptors probably most of the time, one way that they are similar to what we've seen with almost everything we've seen so far is it also has an external signal, okay, that causes and elicits some type of internal change. What was the one exception of all the ones that we've seen so far that didn't necessarily have to have an external signal? Which one? The guanylyl cyclases, the soluble guanylyl cyclases that were activated by nitric oxide. All the others had some type of external signal. Okay, so that was so far that we talked about. All right. So one thing about the integrins is they have to be in one location. What should make sense with the integrins? Where must it be located at in order for them to work? They're within the membrane, right? They're within that membrane because they're used a lot of times for knowing, like, just think about cell-cell contacting, like when cells and others are coming in contact with each other, with other factors coming in contact with the cell, and so they have to be associated with the membrane. Okay, they have to be in the plasmid proteins. Okay? Now, one interesting thing about the integrins that's a little different than what we've seen so far. So these are plasmid proteins. Whoa, didn't realize I hit on that.
Which group do they fall under?
Are you saying that the types?
Yeah.
I don't know if they stick to just a single type or not. I'd have to check that one up, like the type 1, 2, 3, 4, 5, 6. I should say that they fall at least under, they may all fall under one, but I was going to say some of them may fall under two different categories, but they're plasma membrane proteins, I should say. But one thing that's different about them is they can carry signals not only from the outside in, but the inside out. They carry signals both directions. Okay. So they carry signals both ways. Which is important for cell-cell talk, right? Cell. When I say talk, of course I'm anthropomorphizing them, but in order for them really to communicate with respect to each other. This may be a little outdated because whatever year your book came out, but there are at least 24 different types of integrins with unique functions. So at least 24 types. In the beginning they just thought there were one or two. Yes, they're known to help, well, I won't say a lot just in case we go about that. All right. Now, many of them recognize or bind a specific sequence, and that's what's shown up here. It's called an RGD sequence. So that's this next one. So many times they recognize or bind what's called an RGD sequence. Okay. So what do you suppose, what are some of the, let's hypothesize, what are some of the functions you think that could be involved with integrins.
Like maintaining structure?
They maintain structure. Okay, what else can they do? Just think about it. You got your cell.
Communicate?
They communicate. What kind of things are they going to be communicating? They're growing size. Okay? So what happens if the cell doesn't no longer communicates how big it is, and starts to encroach upon its neighbors?
It might explode. It's probably going to explode at some point if it doesn't stop growing.
But I think someone said cancer, tumorigenesis, the fancy word, tumorigenesis. It's involved many times in tumorigenesis, okay? In tumor metastasis. And so these are many times involved in cancers, or can be involved in cancers. Can you imagine? You have the cells growing until they reach each other. They're supposed to stop, and they can communicate with each other. Okay, we need to stop. We need to start to divide, things like that.
So they'll be like typically messed up then?
Pardon?
They're considered like messed up?
They could be. If they're faulty to where they don't recognize it, either they don't, for example, what happens if they don't recognize and bind that RGD signal, or they don't recognize and bind another cell, then they'll just keep on growing.
So
And that's one of the possibilities.
in this case, it's not necessarily over excessive dividing, it's just excessive size, like a large size?
Right, it can be with sizes. So that was tumor metastasis, which I didn't make this. Okay, and so what's another body function that you can imagine that you have to have something binding to signal, not insulin and adrenaline, but what are some just the other, just in general? We talk about cancer and cell growth. And we even had classes on it just recently. So what are some of the other body functions that you can just start to spitball out here? Hopefully not literally.
Anything with muscles or anything like
Not necessarily with muscles. What are some of the special topics and stuff that we had recently? I think some of you guys took this class. Immune response. So many times, many times we're talking about immune responses too. We have something on binding. And so we have, right along with tumorigenesis, we have our good friend angiogenesis, which is just a fancy word for what? Right, growth of new blood vessel growth. And then blood clotting. These are just some of the processes. That's not to say that it's all of them. Remember, there's like 24 different, those are just some examples. We've actually already started talking about a lot of the problems that are involved with the integrins. Okay. So I thought that I had taken the one that had that box on there. One specific type of disease that's associated with integrins, it's called Glanzmann's thrombasthenia. It's a mouthful. So what happens here is it's a clotting disorder. Okay? And so you have a faulty integrin. Whenever you have the smallest injury, it causes major bleeding. And so that's an integrin disease.
Lack of clotting.
The second one that we've talked about already is that, and this should make sense too, that just the opposite of that is you can have a dysregulation of platelet adhesion, okay? So now the platelets adhere too well. They get stuck. I don't have enough room to finish writing this out. So whenever they start to get stuck, they can form arterial blockages, clots. And then finally, you probably have already written it down, but tumorigenesis, that's supposed to be an M. I cannot spell today. Tumorigenesis. And that's because it now has that loss of adhesion in localized areas, so it's going to continue to grow. Okay. Or continue to divide in some ways. Or we've already talked about angiogenesis, is if it doesn't stop blood vessel growth, it'll continue to make new blood vessels, or I should say blood vessels will continually be made, and so therefore you can feed nutrients to help a tumor to grow. All right. Oh, whoops, I didn't show it there. So our sixth class are the nuclear receptors for the steroid hormones. So just from the title alone, what do you suppose is one thing that's unique to them? Their location. Where are their receptors located at? They're around the nucleus and the nuclear membrane and things. So they're not on the plasma membrane directly because of the fact that they're the nuclear receptors. This is why in this little cartoon here, it's a nice job. You'd have its signal that travels through some way or somehow. Which we'll talk, I think we talk a little bit about that in a moment. And then ultimately it's going to go into the nuclear receptor. And so it's either going to be some type of nuclear plasma protein, or we're going to have some type of binding protein that occurs that will ultimately yield transcription of genes. Okay. Before I do this, let me just see a bit. All right. So, the types of, unfortunately these are so tiny for me, the types of hormones that usually, at least in part, that are involved here, one of them one class we've already mentioned. Those are the easiest ones, at least for me to always remember. Those were the steroid hormones. Okay. Then we have retinoid hormones that can do it. Which is retinoid ones, where are they derived from? What compound? Retinoic acid, which retinoic acid is vitamin A. Mm-hmm. Okay. Which, and so these are the fat, they tend to be fat soluble. Just like, remember, I think last semester I taught you the D, because the way we always remember it, the vitamins that were fat soluble, DEAK, vitamin D, which is based off the steroid ones, vitamin E, vitamin A, which is retinoic acid, and vitamin K. And vitamin E, what kind of acid is that one? Well, or I should say, what compound is that one? So we know the official name. It's alpha tocopherol. And so it's much easier to say vitamin E. But those are D, E, A, and K. Those were the four vitamins that were the fat soluble ones. So retinoic acid, so the retinoid hormones. And then finally we have the thyroid hormones that are often involved. And so at least part of theirs, if not the only one, but at least part of it, has to do with some type of nuclear receptor and some type of nuclear effect. Okay. So, examples of these. Does anyone, what's one of the common examples of a steroid hormone? Testosterone and estrogen. Okay, so you have your sex hormones. Estrogen, I don't have enough room to write all of these down, but testosterone, those that are derived from those, so on and so forth. Progesterone, cortisol, things like that. I kind of already hinted at it, but what's one chemical property, physical chemical property of all of these hormones? We already mentioned for D, E, and K. What's their overwhelming chemical property for them? They're what? They're hydrophobic, very hydrophobic. So they are too hydrophobic just to go in this cell by themselves, typically. They're the fat-soluble ones. So therefore, they require special proteins called carrier proteins, typically. This is just showing this little, we'll go over the little cascade in just a moment. Okay. So what happens is the hormone binding triggers some type of conformational change at the receptor. And many times they bind to what's called the HRE. So they allow for binding to the HRE, which is the hormone response element. Which is a sequence directly on the DNA. So that's what this is showing right here. Many times, not always, if not always, I should say, since these are hydrophobic hormones, they can't be loose in your bloodstream. So they're going to be on like your albumin, serum albumin, or some type of serum binding protein, comes in and drops it off the cell. Many times you're going to have a carrier protein that comes and helps out. There are specific receptor proteins in or along the nucleus, okay, that's going to go and bind. The binding of these receptors in this complex on the HRE is what typically will start off and regulates the actual transcription of the gene. So then these genes bind, obviously the transcription forms mRNA. mRNA then travels to the ribosomes to make the proteins. The proteins then are used to make the altered function for whatever that may be. Okay.
Little jelly bean looking thing is the hormone.
The jelly bean. Oh, this right here.
Yeah.
Yeah, that's just their example. The jelly bean.
So on this image, where is the carrier protein?
This one, they're not showing it directly here. Okay, but many times you're going to have a carrier protein along the way. That's going to help out. Just because it won't. They may even be able to go through the membrane if they're fat soluble, but they can't through here. They can't travel on their own typically here because they're going to be, this is hydrophilic environment, so they're going to have some type of help. Okay. Oh. All right. So then I just picked some examples. So the first one, the one on the left, let me see, will they let me? Oh yeah, awesome. These should be pretty simple to see where they're highly hydrophobic. Well, I'm doing a lot of George Orwellian newspeak right now. Does anyone know what newspeak was? You have to read the book 1984. It's an awesome book. You got to read it. What's about the government taking over, totalitarian government. And one thing that they try to do is they try to limit thought by decreasing the vocabulary. And so what they do is they start taking compound words and they just squish them together. So, and they're only allowed to use certain words. It is. It's an awesome book. So, 1984. And so, yes, he wrote Animal Farm is also awesome. But, yeah. Mm-hmm. Yes, and I tried to explain the virtue of 1984 to my wife because we read books and stuff sometimes together and things like that. And I was trying to explain that you can't just start with 1984. You need to start with the appendix to 1984 because it goes through the grammar rules. Because he uses his own language. It sounds really sci-fi, but it's really not that sci-fi. It's just post-apocalyptic in that sense. But So that's why they taught like double think and freedom think and all this kind of stuff. All right, politicians actually refer to 1984 a lot, usually whenever they talk about like despots and totalitarian governments. All right, that's I don't know what he would do. He would just talk about limiting vocabulary by making new words, not making new words, but combining words into just one. Because the idea is you limit their vocabulary, you limit their way of thinking. So, all right, so these are highly hydrophobic. You can see that overall. Mm-hmm. This is tamoxifen. What is tamoxifen used for? It's breast cancer. Mm-hmm. It's a breast cancer drug. It's an antagonist, and specifically, I mean, you should be able to figure it out. It's an estrogen antagonist, which once again means that it behaves a lot like estrogen, but does it have the same effect or does it not? Not. And so you can imagine it binds to that nuclear receptor. Maybe it binds all the way to the HRE, but it doesn't elicit transcription. So it decreases the ability for those genes to be expressed and hopefully, can kill off the tumor cells. So it's a chemotherapy drug, obviously. What are some of the bad side effects, like with chemotherapy in general, but with tamoxifen? Especially in the older, it's been around for quite a while. Right, you need something. The problem is specificity, right? Because you can have hair loss, you can have lots of other different effects, right? And the reason why is if you're taking, this is true with a lot of chemotherapy drugs. In general, if you take it orally to where the bioavailability is throughout your body, then you're going to have unwanted side effects. That's why sometimes if unfortunately insurance are expensive and insurance may not pay for it or they're experimental, if you can do some type of site-directed chemotherapy, then it's usually better. But no, it does. It does. In fact, now, God rest her, I love her to death, but God rest her soul, she actually passed away on my birthday 2 years ago. But my grandmother, many years ago, back in the early 90s, developed breast cancer. She ended up having to undergo a double mastectomy and had to have her lymph nodes taken out and everything. And breast cancer runs in my family. And, but every since then, clear up until her death, because she started to, to suffer a little bit from dementia, not too badly, but it didn't matter what it was, any health problem that she had, she always brought it back and blamed it on tamoxifen. She'll say, well, ever since tamoxifen, ever since. And so we knew, it didn't matter. My grandmother had over 100, grandkids and great-grandkids and stuff by the time she died. But it didn't matter, some type of conversation we'd be having, she goes, well, ever since the tamoxifen. And so we would just always, that was like a running joke in our family. It was about tamoxifen. And it can have lingering side effects, but my grandmother blamed it for everything. And so, the second one is my mifepristone. RU486 is easier to say. Does anyone know what it is? What's it used for? This used to be whenever I was in grad school. This was major news. RU486. Pardon? Yeah, this is the morning after pill. Okay, so my mifepristone, it prevents fetal implantation into the uterine wall, and so therefore, it's the morning after pill. If the woman thought or believes that there's the possibility that she was pregnant, you could take the RU46. There had different dosages. Sometimes it was a series, and what it does is it's a progesterone antagonist. I forgot to put that down, but it prevents any fetus from being able to implant the uterine wall, so then the fetus is discharged externally and then the pregnancy doesn't occur. Okay. All right. Then I always want to pick up the fact that so far we've talked about them where they were exclusive. We had those 6 categories, but life is not always that simple. So we want to talk a little bit. I want to really focus on smell, and if we have time, I'll talk a little bit about taste as well. Because I just think these are really cool. Plus, well, the one for smell has an awesome name. Okay. But these utilize multiple, and you can think about the fact that they're highly specific and highly, what's the word I'm looking for? I can't think of it right now. Maybe it'll dawn on me later. So we're going to walk through what happens This is for cell. And we can see that there are multiple signaling cascades that occur for this one event. What is that word I'm looking for? It's going to drive me nuts now. I can't think of it. It's going to be one of these I'll probably wake up in the middle of the night and I'm like, oh, that's the term. Because it's going to just drive me nuts. All right, first of all, the stimulant for smell is called an odorant. Okay, and that's why they just did it as a little O. What happens is it comes and it binds to a binding protein if it cannot already bind directly to a receptor. So they don't have to have a binding protein, but one way or the other. Then we have the odor receptor, just like what we've seen before. This is a GPCR. And so we've seen that. And anytime you have that, remember the first time it was binding, what happened with the GPCR? It's a good review in general. You have the stimulant, here's an odorant that comes and binds. What happens whenever it binds? Conformational change. That conformational change affects what on the other side? Right, the G protein. And here, this is the G, what would be the GS alpha. I like it because it's called the olfactory G protein, so they abbreviate as GOLF. Within the OLF is the subscripts. But GOLF then hydrolyzes, just like what we've seen before, in the alpha, which was its version of GS alpha, goes on and activates adenylyl cyclase, just like what we've seen. Okay, and so this is nothing new except for the fact that it was an odorant, and they give it, specifically for the G protein, specifically for the olfactory system. Okay, so it's called GOLF. CAMP itself then can go on, okay? And what it does is it activates a second signaling cascade here. So one of its functions here is not just for pKa in that sense, but what it turns on is it turns on gated ion channels within the cilia of the actual neuron. Whenever it turns it on, the calcium channel opens up, so calcium floods in, and this does two things. Calcium then goes on and turns on and activates a second gated ion channel, okay, which is for chloride to flow out. So that's what depolarizes, goes from being a positively charged signal on the outside to a negatively charged signal, relatively speaking. So that's the signal for the neuron. Calcium then, of course, once it's done all of this, if there's too much calcium around, it's going to come back and inhibit itself. And so it's feedback inhibition. So that way it'll close off its own pump whenever there's an excess there. Right? Now, because of this, it does cause for, by closing off its own pump, it causes for a decrease in the sensitivity. And so then it's going to take a little while. You can kind of get used to smell. It'll take a little while for that to reach the threshold once again in order to go ahead and cause this entire process to go through a second time. But so we see here we've got three different signaling cascades, two different types of three different signaling cascades. We have the first one being just GPCR, which ultimately activates this gated ion channel, which activates another gated ion channel, which is what propagates the signal within the neuron. So I thought it was really cool. Of course, the odorants have very specific neurons, and that's why, you can learn to, my mom had just tagged me in a post. All right. This one is for taste. It's not nearly as, what is that word? It's going to drive me nuts. It's on the tip of my tongue. No. I know it's like, it sounds like, but no, I'm trying to think of it whenever someone is like not highly classified, but very, thank you, that is the word. Very sophisticated. See, you got it. We're going to have you playing, Pictionary, whatever, charades on the same team. Sophisticated, yes. This one's less sophisticated, but still, that's highly sophisticated. That's awesome. Are you good at the charades?
I don't know. I mean, I might be, I guess.
Or maybe we're on the same wavelength here, so that's it. Mm-hmm. Which I used to, and this is really a sidetrack, but when I taught Jin Kim, many years ago. I don't know if you guys remember this, but there's something called de Broglie's wavelength, where every mask is off a wavelength. And so I would prove to them that it's possible for people to be like on the same wavelength and things like that, since I don't think they ever got it, because usually they were at that time anyway. But it tickled me. All right, so this one is one for gustation, gustatory pathway, which is just taste. And so once again, we see very similar to in a sense here, but we have this is showing sweet tasting. But we have the signal here binding its G protein, and its G protein is they abbreviate for G-gust because it's gustducin, means a transducer for the gustatory pathway. But G-gust isn't nearly as fun to say as golf. But that's beside the point. But otherwise, it's the exact same principle here. So we have the conformational change. It activates a GS alpha subunit will go on. Our good friend adenylyl cyclase will then convert CAMP. CAMP then goes on, and here really is PKA. PKA is activated. But what we see a little different here is PKA, the way that it works is it phosphorylates a potassium channel, and by phosphorylating, it actually closes it. And so its depolarization is the opposite of what we see with smell. Okay, so therefore, the way that it causes the neuron to propagate the signal is the fact that now there's less positive charge that's normally flowing out that's stuck on the inside. Okay. Once again, there's still multiple pathways that are involved. Okay. Are there any questions on these, just in general? Okay, because that's the end of the chapter. And like I said, normally this would be the end of Biochemistry 1.